Engineers HVAC podcast. I am Tony Mormino, your host today. So this is a double super fun episode here. So we are live on LinkedIn. Number one, filming this. Excuse me, I got a little frog in my throat. You can tell we're live by my voice. And we also have one of our guests live on the factory floor with Nyle Water Heating Systems. And Nyle makes heat pump water heaters for commercial applications and for residential. But today we're going to talk about commercial applications for heat pump water heaters, which are in the news. And the way this is gonna roll is Chris is on the factory floor, which is loud. He's trying not to get run over. He's trying not to get hit with hammers. So we're gonna jump right into a quick interview with Chris. Then we'll talk a little bit more about their experience and about where we are. Well, we're in Maine. He's in Maine, Bangor, Maine. But Chris, while you're on the factory floor, give us a quick rundown of what we're looking at. Let's do a little factory tour while we're here. Take it away, Chris.
Awesome. Thank you, Tony. It's awesome to be here. So wanted to give you all an opportunity to see kind of behind the scenes of what a heat pump manufacturer actually looks like and what it looks like to build something in the United States these days. So this is our factory in Bangor, Maine. Standing right behind me here, you'll actually see several heat pumps in the process of being built. We have a number of projects coming across the line, all leveraging this exact model. This is our C185 air source unit. You can see inside here for those that know a little bit about heat pumps. The refrigeration circuit is currently being built out, as well as our potable water side. So you'll see our condensers over here. We've got our evaporator and all of our associated pipework, our receivers, and our compressors. So really awesome unit actually to see being built. This is one of the most compact air source heat pumps, especially in the high temperature realm that you'll see. Very deep coil on this one. A lot of capacity for a very small footprint. Once they're built up, you'll see that they actually have a closed panel on top so they can be stacked. Very cool for inside mechanical spaces. And for ducted applications, places where traditional heat pumps would be a little bit tricky to deploy. So any questions, Tony, on what we're seeing here and things I can point out for your audience?
Yeah, thank you so much. And we're going to show pictures of what that looks like finished in a mechanical room when Chris goes to the back presentation room. But so just so the viewers understand, this is an air-cooled heat pump water heater. So we're making hot water with this unit by using electricity through a heat pump, correct?
Correct. And so this is a very special heat pump, and this is what we do here at Nyle. We build high temperature heat pumps. So these heat pumps are designed to take air temperatures from as cold as 10 degrees Fahrenheit to 120 degrees Fahrenheit and take that heat and convert it to water or into a heat or to 160 degrees or less for heating water. So a lot of our applications are going to be domestic hot water, but really anywhere where higher temperatures are desirable for water-based applications, that's where you're going to see our heat pumps. These are behind me, like I said, these are air source heat pumps, although we do build a lot of water-to-water heat pumps as well.
And Chris, what would you say is the biggest difference between a water source and air source heat pump?
Well, it's all in the name, right? It's where our energy is coming from. So when you go into either heat reclamation or more temperate climates like the coasts, where we're talking the Pacific Northwest, California, on down into the south, and Tony, this is extraordinarily common in Florida. We tend to put air source heat pumps outside because the weather is nice all year long. You know, kudos to you guys. I'm from Chicago, where it's currently below freezing. But that allows us to extract that energy in those nicer climates and bring it indoors and use it for, in our case, for high temperature heating, HVAC side, we use it for space conditioning purposes. But that is the low hanging fruit of heat pumps, is being able to just plant a heat pump somewhere and extract the energy from the ambient air. There are, as we get into commercial applications, there are a lot of opportunities to leverage what we call water source heat pumps. So in the residential world, we talk about geothermal. That's traditionally all employed through water source heat pumps, where they have a geofield and they're extracting energy from the ground, and it's all run through a water loop. So your heat pump extracts energy from that water and then moves it to another water system, or sometimes we go to water to air. In commercial buildings, we have other water sources available to us, whether that's a boiler loop, a chilled water loop, condenser system. There's a lot of opportunities to leverage existing infrastructure, gain efficiencies in those systems by chilling that water, and then we use it to make domestic hot water. Um, to your point, biggest difference there, where's your energy coming from?
And
Great explanation.
are there some size differences between the units? And if so, why is there?
Yeah, absolutely. So the biggest driver of sizing of a heat pump is the size of its compressor. How many tons it's going to offset either on heating or cooling. In our case, we are exclusively making machines that provide heat. HVAC, talk a little bit more about cooling. But inside this particular unit behind us, our C185, that's a 185,000 BTU air source unit at its nominal rating. And that's driven by the size of its compressor, which in this case is a 20 horsepower compressor. When we get into other size classes, you go to like our E360, which is a 30 horsepower compressor, or we've got our little C90 that's operating on a 15 horse compressor. So all the units spanning all different sizes, that's what's going to be the major driver here.
Excellent. And is it possible Landon could just do a quick view of the inside of that unit while you audibly tell us what he's looking at? Is it possible there?
Absolutely.
I don't want to get y'all in anybody's way, but
yeah, come around the side here. So kind of looking through everything here. We have our compressor all already wrapped up, ready to go here. We've got our receiver. This is our condenser. So we're taking energy from the air in this evaporator. So air, and actually I'll bring you around, Landon, so you can see exactly what we're talking about. This is a traditional evaporator coil that you'd see on any space conditioning equipment. We're extracting heat here, cooling that air down, transferring that into our refrigeration circuit. We then transfer that energy to our compressor, which takes that energy and compresses it, which creates that heat we're looking for. So we'll take that 40-degree ambient air and turn it into 140 to 160-degree water. We then take that, send that refrigerant to our condenser over here. So this is a brazed plate heat exchanger, double wall, for potable applications. It exposes that extraordinarily hot refrigerant to the water, heating that water as it passes through the unit and providing that temperature out to a storage tank or whatever you may have from a storage media. We do have a couple different configurations here. This one in particular appears to be a multi-pass. So this unit is going to operate exactly like an indirect fired boiler. So it's just going to dump BTUs into a storage volume as quickly as it can at a set delta T. Our single pass machines would add a control valve in here, which is going to modulate the flow on this pump, controlling the outlet temperature. So we're going to maintain a precise outlet temperature, which gives us some advantages when we get into actual applications. So a little bit different, or a little bit different internally when we get into that type of machine.
And if you were looking at the inside, Chris, of a water source unit, what would be the difference?
Biggest difference is this evaporator here. So this, in order to extract heat from air, you need a lot of air at a very high flow rate to constantly be moving across this coil. When we get to water is much more energy dense. So in those water source units, we actually make a C185 water source unit. And it is about 60% the size of this housing for the same amount of BTUs. So we take all of this out, we take the blowers out or the fans out, and we're left with just 2 brazed plate heat exchangers like the one that you saw inside the unit there to allow us to extract the heat from a water source and then apply it to the refrigeration circuit, just like you do in the cycle we already described.
Very cool.
Excellent explanation, Chris. Well, do you want to move on to something else on the floor there? This is great stuff. Thank you so much.
Sure, you got it. We'll move past engineering here. There's a little impromptu meeting happening, so we'll get out of their way.
This is the real story behind manufacturing right here. We're not just showing you a catalog here. We're showing you the real deal.
So we're currently, those are all of our work in progresses on this side of the building. And actually, Landon, I'll let you just kind of pan across the floor here. So kind of on our left is all of the machines that are in various stages of being built, and on the far right is the goods that are being stacked, ready to be built. So you see we have a lot of this particular unit being built right now. Now we'll go ahead and kind of pivot back around, and I'll show you where all of this product ends up at over here on our test bench. So one of the unique things about Nyle is our commitment to quality and making sure that when we send one of these high temperature heat pumps out into the field, that it works on day one. That means that we run every single unit here at the factory, we pressurize it, we run it at temperature to make sure that it does exactly what it's going to do. We log all of that information here and save that in perpetuity for our customers. So absolutely incredible quality control here to make sure that what we say these things can do, they actually do. I currently have a unit waiting to be tested here. This is one of our C250s. So this is similar to the air source unit we already looked at being constructed, but slightly larger. It's a 250,000 BTU unit, really designed for rooftop applications in warmer climates. So you see a lot of these in California, Florida, etc. We've got vertical discharge coming off this one where the airflow is going up. We've got dual evaporators, one on each side of this particular unit to give it a lot of surface area for its given footprint. Kind of pivoting back over to this side, you'll see actually here's a C250 that's currently being tested next to a much smaller air source unit. This is a C90 up, and we just kicked on. I'm sure my audio just got super dampened.
Sounds great.
Sounds great.
What's awesome here is that I am standing 5 feet away from this thing while it is running, and I can still talk to you. So these units are incredibly quiet. Something to take a great deal of pride in, and we continue to innovate and make strides to make them even quieter.
That's really good. No, you're coming in loud and clear. Actually, we can hear you just fine. Normal factory noises in the back. And if you're just tuning in, what we're looking at here are air-cooled, air source water heating units, water heaters, heat pump water heaters. Oh my gosh, I tried to get that out. I'm not even on the factory floor and I'm struggling, but they're air-cooled heat pump water heaters is what we're looking at for commercial applications. So,
and to Chris's point, these are absolutely fantastic on sound, and that is very necessary these days, especially as I know very intimately in California. They do not want these very loud. So look at how close we are to these units, and you can barely hear them. So just when it comes to the sound they're kicking off, these are absolutely fantastic. And this C90 is a very popular unit of ours, all the way from Hawaii to California. So it's very cool seeing those being built right now.
Absolutely. And so we'll pop over here too so you can see another variant. So that was an axial air source unit. So it's a traditional fan. Over here, this is one of our C185s that's going through build right now that actually has a blower installed. So this has been an option for quite a while on the C185, but one thing that's unique about our heat pumps is their flexibility in installation. So we try to provide an installer a packaged heat pump that is a water heating system in a box. So that when it arrives, they're hooking up the domestic water to this thing, and immediately they have what they need to produce hot water. That means that the units are going to get put in a wide variety of situations, though. So traditional heat pump manufacturers, the most often going on rooftops when we talk about air source units. And that means lots of fans, low static. They're just taking air from around them and discharging it in whatever direction they deem necessary. These particular units are very popular, though, in parking garages, where, especially when we get into colder climates, it's a little bit warmer. Inside the garage, you got all that thermal mass from all that concrete, all of the cars putting off heat. So there's an opportunity to get more efficiency, more energy, but you have to fit into a place that traditionally heat pump wouldn't fit into. So you would install this in that space, and then this blower actually gives us a lot of static so that we can push against ductwork and duct this thing in and out of the space. So lots of flexibility there. Already mentioned these are popular in that space as well because they're stackable. They're very short once they're employed, and it is a very useful form factor.
No, that's great, Chris.
One thing too, while we're out here, I want to give credit to our manufacturing team. And actually, Landon, if you take a look at the heat pump and look down on this one, you'll see that Nyle is very, very focused on lean manufacturing techniques and not building lots of monuments inside of our space, so we can be flexible in what we build and when we build it. So looking around us, we've got a couple of cranes that are bolted to the floor, but everything else is mobile. So our team has put every heat pump on a rolling skid that's at the appropriate height for the build. That allows them, so if something, if we're missing a part and we're building a unit, we can pull it off the line, and we don't have conveyors, we don't have all this moving machinery, we don't need a forklift. And that allows us to, again, keep things moving, keep product on going out the door. That has enabled Nyle to do some things that are absolutely unheard of in this space, which has continued to deliver units all throughout the supply shortages of last year. And then ultimately at this year, we've had lead times as low as 8 weeks on heat pumps. We can actually build heat pumps faster than most boiler manufacturers can build boilers. So this is...
what's the current lead time?
So currently we're sitting at about 14 weeks. I'll give a little ribbing to Copeland while we're live here. We're waiting on some Copeland compressors. Hopefully they hear this loud and clear. Usually we don't have this much work in progress on the floor, but they are coming through, and we'll be moving units out just a little bit delayed from their initial delivery dates.
All right. So if the president of Copeland's listening, let's help out the Nyle folks in Bangor, Maine, and get them some compressors. So they're only behind. They're only a little bit late because they're such a good company and such quality product. Right?
Exactly. We value their partnership.
100%. 100%. Awesome.
All right.
Well, Chris, I have a bunch of questions for you, but I'm going to save them for when you're in the back room. Is there anything on the factory floor? Anything else you want to show us?
I think that's all I have for the moment, unless there are any questions out here. Again, I don't want to continue to be in these guys' way. They're being really generous with their keeping up the background.
100%.
Just one question for you. So now that psychrometric chamber to test the units at elements. Can you explain a little bit about that? And obviously, it's not seen in this video, but I think that would be a good point to cover.
So Nyle Water Heating Systems currently operates across 2 facilities. This is our primary manufacturing floor, but we also have a portion of our R&D at our parent company, Nyle Systems, on the other side of the river, about 15 minutes away. And that's where our psychrometric chamber is. So we have the ability to test air source units specifically at a wide variety of test conditions. So basically, when you buy a heat pump from Nyle, we have the ability, and we put this information out on what a system is going to actually do in the field, not just back into what the compressor says it could do at various duty points. So we do pride ourselves on the quality of the data that we put out in the marketplace and how it helps the engineer provide a design that will perform to the level expected. So that particular chamber, though, is it's about 30 feet tall, 30 feet wide, and 50 feet deep. And that an air and volume enables us to cycle a heat pump of this size for a long duration and make sure that we can get test conditions we've gone as low as 0 degrees inside of our test chamber all the way up to over 100 degrees. So that allows us to run the entire gamut. We're actually upgrading the humidification over there right now to allow us to really hit saturation at near freezing conditions. So we'll be able to actually do that testing indoors. We've actually been doing a lot of that testing outdoors because lovely Maine encounters those conditions around 40 degrees here as well. But we'd love to have a little bit more control for our defrost testing that we do.
That's a great segue because I have a video you can walk us through when you get back into your comfort.
Awesome.
Why don't we let you go back into your control room there, and we'll continue this presentation, talk about some applications. And as Chris walks back, again, Tony Mormino, the Engineers HVAC podcast. I've got Tomas Novillo here. He's with Nyle Water Heating Systems. And Chris Ebener is also with Nyle Water Heating Systems. And what a great treat today. I was going to interview Chris and Tomas, and he said, "Hey, you mind if we walk the factory?" I was like, "Mind? Like this is like content heaven for the marketing guys." So thanks for giving that walkthrough. That was super, and really enjoyed that. And Nyle Water Heating Systems You can look them up online. And if you're watching this in the future on the podcast or our YouTube channel, you can look in the show notes and I'll put links to Nyle. You can go check them out. Heat pump, commercial heat pump water heaters. They do make residential products as well, but we're talking about mostly the commercial stuff today. And as most people watching know, and heat pumps are in the news big time now because of electrification and decarbonization and alternate ways to heat water. And if you got a commercial building, you got a couple options. You got gas and you got electricity. Maybe there's some solar and stuff too, but for the most part, you've got those two options. And I wanted to talk a minute about heat pumps and why does electric heat pump make sense over like just using a heater, a electric strip heater to heat your water, and I equate that to your home unit, right? I've got an electric water heater at home for my home water, but I have an air source heat pump for my heating. And when we talk about heat pumps, we're generally talking about COP, the coefficient of performance, in terms of the efficiency. So the higher the COP, the more efficient it is. The COP of electric strip heat is generally 1. The COP for heat pumps could be 3 to 5, maybe even a little bit higher, depending on the application. So the big thing to note there too is, with a heat pump, you're moving BTUs. With electric strip heat, you're creating the BTUs. So go ahead, Tomas, you had a comment about that.
Yeah, I was going to say, coincidentally enough, yes, the range is generally 3 to 5, but with our water source units, we're actually able to hit a lot higher than that, anywhere from 8 to 13, depending on how these units are set up and connected, which a lot of the versatility of these could actually improve COP to the unit connected to them. So you create these systems that they're connected to and everything could increase. So we're seeing vast improvements on that side, and we're really excited as this continues to grow. We're excited to show what we're capable of, and taking more energy off the grids is only going to help us. So that's something we love about what we're doing out there and our versatility with that.
Awesome.
Yeah, this is also a great segue there. So again, why are they in the news? It's because there is no commercially available way to move energy or create heat or cooling in buildings, whether they're commercial, residential, industrial, than heat pumps. Heat pumps, one of the unique things about Nyle is that we have been building commercial and industrial heat pumps since the 1970s. It's so the only thing that we do. And that's, people say, well, heat pumps are a new thing, or heat pump water heaters are a new thing. Well, we go, well, no, we've been doing this for a long time, waiting for everybody else to acknowledge how great heat pumps are.
Waiting for everybody to smarten up, right? When is the world going to get onto this thing? Now you can't keep up with the demand, right?
Yeah. And that's, again, one of the unique things about Nyle is we've done a great job of being able to keep pace with what the market's asking for. And are well positioned to help people make this change to where their heat is going to come from. So excited to dig into any and all topics here. Where do you want to go?
Let's talk applications. I'm an engineer. I'm watching this, and what kind of applications am I looking out for? What should I stay away from? You could talk vertical markets. You can talk in any aspect of that you want.
Yep.
Actually, you know what? Before we do that, I changed my mind. Before we do that, let's talk about the two different types of. This is what happens when you go live and you don't plan. You kind of just go. Well, let's talk about the two different configurations of heat pumps real quick. Can you just run down an air-cooled heat pump versus a water-to-water heat pump? And I'll start that off by saying, I like to just put it in terms of your home unit. Like a lot of people are familiar with a split system air source heat pump in their home. I have two. Yep. In my home, I have one in the basement, one upstairs. And basically what we're doing in the cooling mode, in the summer mode, is you're cooling, taking heat from the inside and you're moving it to the outside, rejecting it to the relatively warm atmosphere, right? Mm-hmm. We don't do that with your product. We're just heat pumps. We're not doing cooling inside or cooling the water on the inside loop. Okay. I'm probably confusing people, but basically, the distinction I'm trying to make is there are some products, what we call heat pump chillers, which are chillers one day, and then, I think I'm going to make hot water the next day, which is fine. Certain applications, that's fine. The product we're talking about here is a pure heat pump water heater. It's a water heater that uses a heat pump cycle.
Yeah, correct.
Okay,
We
so I jumbled
we
that quite a bit. So you clean it all up for me. I'm giving it to
you
you.
got it. I like to quote one of our reps from the Pacific Northwest is we bring the heat. Um, so in terms of heat pumps, you're right. The vast majority of heat pumps are either cooling dominant. So think your home refrigerator or your air conditioning coil. Or they do both. They heat and cool. So they'll cool when it's hot or when it's hot indoors, and they'll heat when it's cold indoors. They're just moving heat from one place to another. Our heat pumps are designed to tackle a very specific challenge, which is replacing existing gas-fired or electric-resistive products that are they're only for heating. So this is traditionally, in your home, that's domestic hot water, or for large swaths of the country, they're boilers. So you're talking, the heat, the way that you hydronically heat your home. So this is a technology that in many ways is a drop-in replacement for that type of product. Now they are fundamentally different. Gas technology is very different from heat pump technology, and that's one of the challenges the industry has. And that's one of the areas that Nyle really helps the engineering community and its customers is navigating those differences.
Excellent. A few questions here we can go through. And then we'll talk about applications because I kind of jumped around there for a little bit. But is it normal to use heat pumps for a water heater in Florida?
Yes. So again, residentially, air source heat pumps stacked on top of a tank are getting more and more common and more popular. That application is fairly well defined. Those products have been in the market for quite a while. But the commercial side really has taken off over the last 6-7 years and really built up over the last 4. So in terms of what's happening in Florida, what's happening from Illinois, there are places where it's still fairly foreign to them. But the areas that have been doing this the longest, Hawaii is a great example. They've been putting heat pump water heaters in for 20 to 30 years. We're actually at the point now where we are providing replacements for technology that was deployed 30 years ago for heat pump water heaters, which is an awesome state to be in. But even transferring over to California, areas of the Pacific Northwest, Seattle specifically, Vancouver, British Columbia, heat pumps are extraordinarily popular in those regions, and we've been doing a lot of commercial work there for a long time.
Excellent.
And we're actually doing, surprisingly enough, work in the center of the country with geothermal projects. I absolutely love the federal rebate that they have on geothermal right now. So our water source units are being put in places that might have otherwise not be seen as a heat pump market. One of my favorites came a couple years ago, Lincoln High School. So it's very cool to see in Lincoln, Nebraska, them utilize the federal rebate for geothermal and move that direction. We're seeing it really come up all the way, Dallas and those parts of the country really that have the geothermal opportunity really picking up steam with heat pumps, and that's very exciting for us.
It's always cool to put in a water source heat pump in a place that gets to be negative 35 degrees Fahrenheit during the wintertime. We do a lot of work in central Canada with water source heat pumps.
Yeah, so that's a good lead into a question here by Anusha. I hope I'm saying that name properly. Please talk about the vapor compression ratio on a heat pump at lower OA temperatures. So just what you were saying. Let's talk about that. These won't work under if it's colder than 30 degrees. Heat pumps don't work, right? Like we hear that all the time. I'll let you answer that question.
So actually on the screen, it keeps rotating past on our website there. There is one of our products, our E360. So it's a 360,000 BTU air source unit that's designed specifically for mild cold climates. So that particular unit can produce 140 degree water at 10 degrees Fahrenheit at 100 degrees of lift. So it can take cold water at 50 degrees and make it 150 degrees. It's an absolutely incredible system. And a lot of this has been enabled by technology improvements in heat pumps, specifically in compressors. But even in refrigeration design, there are a lot of new techniques that have been made available over the last 5 years to allow us to build heat pumps that can do incredibly well, even at very low ambient temperatures.
Yeah, I think there's a myth. I grew up basically in the Southeast, and heat pumps are in our blood. They're just normal, everyday units for us. But as the decarb and electrification kind of takes off, we get a lot of questions from the northern climate. Do these really work up north? And I actually had a guy reach out to me who runs a contracting business in Colorado, and he wanted to come on the show. I was like, great, come on and talk about heat pumps and low ambient conditions. And I know it gets a lot colder up in Canada there, but yeah, they work just fine in cooler climates if they're designed. Make sure they're designed for that. Make sure to check with the manufacturer. Not all products are created equal, as they say.
And let's talk about that too, because that's part of the myth here that we are all working with is, so Nyle works on medium pressure refrigerants. So we've traditionally we've been an R134A manufacturer, and are currently working through the transition to R513A. Again, very similar refrigerant, non-flammable, A1 classification. Really wonderful refrigerant for us. It enables us to work from a quality platform we've built over the last 30 years, and make sure we're not having to do anything radical or that's unproven. It's been really positive for us, but it is fundamentally a different refrigerant than, say, 410A, 454B, all of the kind of lower pressure refrigerants that are being used in most heat pumps. So in order to create very high temperatures at high lift in these applications, we are utilizing a fundamentally different refrigerant to accomplish those goals.
And I missed that, Chris. What was the refrigerant you're moving to?
R513A.
And
low GWP. Yeah, go ahead.
I was going to say, that move has already not only begun, it's almost finished. That is a full transition that we've already started and almost come to the end of. Chris, I have a question for you. Why did Nyle decide not to go with CO2? And what have you seen in the market as differentiators between CO2 and 513?
Yeah. So, there's a lot of bullet points here. Just real quick on 513. It's low GWP, SNAP compliant. It checks all of those boxes for those that are paying attention to what's going on with the refrigerant alphabet soup we deal with on a daily basis. But in terms of alternative refrigerants and high lift, low ambience, there are other refrigerants that can do this. You mentioned CO2. Propane is another one that's being talked about quite a bit. Each one of these, everything has its pros and its cons, right? CO2 specifically can make some pretty exotic claims at very low ambience, and that's pretty incredible. Unfortunately, it comes with downsides. And I won't get into the weeds here, but do your research, right, on what's actually happening when you drop below a certain range. I've already mentioned one of the great things about 513A for us is it allows us to take that knowledge we've built up since the 1970s on our refrigeration systems, reliability, supplier relationships, and parts availability, and use all of that to our advantage when we go out into the field. Again, one of the key things I want to make sure that everyone's on the same page with decarbonization is when you go and put in a new product that is more efficient, one of the driving factors needs to be, well, what's its life cycle? What is its impact across its entire lifetime? And we want to put in a heat pump into a building to drive efficiency, but we also want it to last for as much as 30 years. That's a big commitment to a building. A traditional water heater, it's 10 years or less, right? So we're in this to not just make a short-term gain in efficiency, but also a long-term impact from the life cycle of the equipment. So we want to make sure we're putting out equipment that's going to last, that's going to perform for the long haul, and that's extensively maintainable. So we use name brand components from large manufacturers, things that are available and will continue to be available for a long time.
Excellent. And a few comments here. Shout out to Clifton Beck, who's watching with ESCO Institute. Clifton does a lot of training and has been on our show a few times. Thank you for commenting. He said, I'm excited to see U.S. manufacturer already going to 513A. And I have to do my research. I'm not familiar with that refrigerant, so I'll have to do some research on that. So thank you for explaining that to me. We did get a question, which I thought was interesting. Can we use these heat pump water heaters to feed radiators?
So this is an area where, yeah, at the end of the day, heat is heat, right? So we can make heat for those types of applications. We do specialize in domestic hot water. That is what we specialize in. However, we have continued to do more projects in hydronic heating because honestly, it's a rare find to find a company that can handle the conditions for that space and also produce temperatures between 140 and 160 degrees consistently. So one of the orders that's being processed out there right now for those C185s actually is for a radiant heating application. We are doing a deep energy retrofit on a very, very large, inefficient building that has 100% exhaust air. They use zoned VAV reheat year round. And it's an all steam building. So we're part of a project to put in a recovery chiller and then eliminate, I believe it's 18 steam heat exchangers throughout the building for the VAV system. So they're taking those heat exchangers out, they're putting our heat pumps in their place to generate the hot water directly to that radiant system and extracting the heat from the waste air for the building. So we're taking that air that's running out the building at 70 degrees, typically, maybe 65 at the wrong time of the year. And we'll drop that temperature by 25 degrees on its way out of the building and use that heat to reheat the building. Absolutely incredible COPs, absolutely incredible application.
That COP's got to be insane at those high evaporator temperatures, right?
Yeah, you get year-round 70-degree air for the most part. That's very, very cool application.
Oh my gosh, it's not in North Carolina by any chance, is it?
I know.
I got my
DC
video camera batteries charging up for that one.
DC region, so not too far away.
Yeah, not too far.
Awesome. Well, that's great. Well, that's a good lead in this applications. Like, what are some common applications we see today with this product?
Yeah. So most common applications that we literally do all day, every day are multifamily applications all across the U.S. Low income multifamily in particular has been seeing a huge uptick over the last 2 years with some of the funding that's become available in order to drive decarbonization on an equity basis, making sure that we aren't saddling our new construction for low income housing with inefficient systems that may be phased out in 30 to 40 years and just kicking that can down the road. So we do a lot of work in that realm. We also have continued to do a lot of work in healthcare, government buildings, office buildings. I mean, anywhere that uses a considerable amount of domestic hot water is our sweet spot. We've got unit packages from, again, 90,000 BTU air source units up to packages of millions of BTUs in water source units. So, and we do staging, we have, central controllers, all of that thing to allow us to multiplex systems together for just about any application you can imagine.
And I'd say on top of that, one of our most popular applications to add is colleges. Colleges have been loving us from coast to coast, and been great applications for dormitories and other facilities on campus. And I'd say one other that comes to mind would be national laboratories.
Yes.
Awesome. Loving us from coast to coast. That's another good tagline. Heather Robinson's our brand manager, and she's watching. She commented, I love the bring the heat. We bring the heat. So you might be seeing that on our website somewhere. She might be making up some shirts or something with that right now. So
I like it a lot.
That's really good. Another interesting application. I was talking to the Armstrong folks the other day, and they said they're seeing, and I had to Google this because I hadn't heard of it before, but data centers use you wouldn't think a heat pump. What would a heat pump water heater be doing in a data center, right? But, as everybody knows, they put off tons of heat, like tons of wasted heat. So if you build that data center close to a population source, you can cool the air of the data center, take those BTUs, heat the water, and use that hot water for domestic hot water heat, which is basically free minus the pumping and all that. It takes the right kind of scenario of, unfortunately, the land near populated areas is very expensive. So that's why these data centers are usually in more of a remote area. It's my understanding. I'm not a data center expert, so don't comment. Give me 50 comments on that. I just lost my camera. I'll fix that in a second. But so have you seen data centers, anything like that? Or why don't you talk about that while I fix my camera?
Yeah, that's an excellent segue into district energy. So as we look at the future of buildings and even the buildings of today, taking heat from one building and transferring it to another, or cooling and transferring it to another, is a tremendous opportunity. So we're seeing this in high rises in downtown areas where the buildings that are facing the sun are in an active cooling. They take that energy and move it from one building to another that is in need of heating. So it could be, 40, 50 degrees outside, and a high rise, all glass and steel structure is incredibly hot on one side and needs active cooling. So rather than just take that energy and dump it outside, and we can take that, bring it into a central loop, move that energy from one place to another, and use it intelligently. For domestic hot water, we can use it for heating those other buildings. There's all kinds of applications there. And so, the data center market, the big players there are, and I know there's a lot of work being done to use that energy intelligently. And that's incredibly exciting. We're also seeing that too, even at the residential level. So there's a few towns, upstate New York, and areas of the Northeast that they're actually, the local gas utilities are trying to figure out what their future is. And they're doing piped geothermal for residential level applications like commercial applications. So instead of a gas line coming into your house, you have a piped water return, and all of the geothermal infrastructure is owned by that utility provider. They have all the technology, they have all the boring technology, they have all the knowledge on sub-metering and long-term infrastructure. They have the mentality around, I'm going to make a 50-year investment and right now, and get paid back over time by the utility payers. So those projects are incredibly exciting. That's, when you talk about solutions for extraordinarily cold places, that just makes sense. So anyway, I love talking about that stuff.
Yeah, me too. I got so excited when I heard about that. At least the data center part. I Googled it and I was like looking into it. So if you're watching this and you're building a big data center, call us. We'd love to at least talk to you about it and give you some budgets and look at that as an opportunity. So that would be fun. But real quick, hey, Dave Recca's watching us today. He's with Aon and he has a question. Is there a specific approach to water side scaling that we would recommend to prevent that?
That's a good question. So I actually I have a water quality background, and specifically to domestic hot water. We utilize our double wall brazed plate heat exchangers. We maintain fairly high velocities across those heat exchangers in order to keep them as clean as possible. But like any heat exchanger, they have limitations on water quality. Number one thing for a brazed plate is, obviously, to your point, calcium-based scaling. That's a softening question. There is the traditional forms of softening that have been employed for decades at this point. There are also new ways that have come through for salt-free conditioning that can make a huge improvement. And honestly, filtration technologies have come a long way to be cost-effective for these types of applications to protect those heat exchangers. Liquid line or separators. I'm utilizing refrigeration speak to talk about water stuff, but fluid separators, mechanical screen technology, cartridges, bags. There's a long litany of things you can utilize in this arena now to protect all water bearing equipment, not just the heat pump, but allow the equipment inside your facility to last longer, be more efficient and more effective with less manual cleaning.
And to that point, what would you recommend, Chris, on a, let's say, dirty water situation when you're tied in with our water source units in a condenser water loop? What would be the recommendation there?
Yeah, so that's a very unique edge case that most people don't think about until they come to a project where they're doing it. But we do get employed a lot to cool the water off of a cooling tower, right? There's a ton of energy that's just rejected outside on a regular basis to a tower. So it's actually extraordinarily common in Hawaii. We tend to put in a low fouling heat exchanger on the condenser system, or on that condenser water, and then run a secondary glycol loop for a source for the heat pumps, so that the water quality is separate, and you can use an optimized heat exchanger for those applications.
I have never heard of that for a heat pump. So let me make sure I understand that. So I've got a chiller plant.
Mm-hmm.
I've got 95-degree condenser water design, whatever. You're taking a side stream off of that, running it through a heat exchanger.
Yep.
Pulling the BTUs out of that through your, what we would call the condenser and the heat pump. Is that correct?
Yep. And then discharging that cold water back to the heat exchanger, and you're chilling that condenser water on its way to the tower.
That's so cool.
Yeah. It's just, keep the energy inside the building as much as you can. You've already paid for it.
So you're taking the BTUs out of the tower, entering water conditions that is going to be cool. It's going to be cooled anyway. You're going to be removing the BTUs anyway, right? So it's heat that we would normally reject to the atmosphere, but we're pulling it out of the water, putting it back into the system.
Correct.
Wow, I love it. That's so cool.
And Chris, what's the other side of that? There's some big projects going on in Florida right now using the opposite side of that. Can you explain how it works when we're not tied into the condenser water side, but the chilled water side to a chiller?
Yeah, absolutely. So the other beneficial side is obviously taking the energy away from the water that comes back to the chiller. So this is, Tomas mentioned some pretty extraordinary coefficients of performance. This is where those come in, where we're a heating only appliance. A chiller is a cooling only appliance. We are a match made in heaven in many cases, where we can take all of that return water before it comes back to the chiller to be operated on, drop its temperature even further, giving an increased coefficient of performance to the chiller. So taking advantage of those cooling BTUs from our system, and then giving us tremendous performance as well on the heating side. It's those systems, it just depends on where you have more heat, right? Is there more heat on the tower side, or is there more advantage to going on the chilled side?
That's awesome. I've done several jobs on the chill water side, a side stream. We used to call them heat pump chillers, but I've done a bunch of those, but I've never done one on the cooling tower before. That makes more sense probably, but I guess it depends on, it's one of those answers we like to give. It depends. Like, which one's better? Well, it depends. You got 45 minutes to talk through it,
Yep.
And, someone made a comment earlier that I meant to address in the chat here about, when you're looking at this, and he had a home example, like you're looking at home, it's more expensive. People don't want to pay the extra. Well, yeah, it's all about the return on investment, right? It may be more expensive. Sometimes there's incentives involved, but sometimes it's maybe more expensive on the front end, but there's a 2-year payback, and then you're making money after that. So it's just like any other. There's engineering trade-offs to every type of technology. That's for sure.
I'll circle back to that hydronic project that's being built on the floor right now. The primary advantage of that system for that particular building was the fact that they had just done a retrofit of all their existing VAV system for hot water between around 160 degrees. A traditional heat pump would not have allowed them to provide heating at that level. They would have had to go through and rip out all those coils. So in this case, we're a little bit different. We can come in, provide the temperatures they're looking for, and they don't have to replace all of that existing infrastructure. Each application, you have to look at the entire picture, right, on what makes sense.
100%. It depends is the answer, right?
It depends.
And one thing I would love to cover that is I would say an industry point that everybody needs to acknowledge, and that's education. I think that the whole entire industry is a little undereducated on certain things. And Nyle, we have a big, I would say, exclamation point with our partners and contractors in the industry to really help and support and train them this year. I think that we want to be a company that is looking at the piping. We're looking at, hey, how does your design going to fit? Are you using the right type of tanks or using the wrong type of tanks? There's so much in this where you can't tie these in like traditional water heating systems. You really have to understand that this is a very big mixture of the plumbing side and the HVAC side. And there's an educational piece that isn't quite hit on there. And Chris, can you explain a little bit of how we've tackled that and what we've seen go wrong in the industry currently?
Yeah, absolutely. So, heat pump deployment, and I mean HVAC has been doing this for quite a while. Their problem set is very contained, right, to that particular problem. When you take that application knowledge and try to apply it to domestic hot water, as a perfect example, the temperatures are different. The use case is different. Space conditioning is a constant load. And you're just trying to balance back and forth between the operating conditions in order to maintain that constant load. Domestic hot water is a dump load. It happens, it peaks and then has extraordinary valleys. And on top of it, our industry on the domestic hot water side makes decisions based on some very arcane principles. Familiar with the term the Hunter's curve, right? This is something that we've been utilizing to size domestic hot water systems for a very long time. And it's a series of assumptions that are very old on high flow fixtures, on extraordinary use cases, 100% loads, things that just never happen in buildings. So we're having to come to the table and say, okay, all that stuff you used to do to size boilers, we're not going to do that anymore. Because ultimately you're going to end up with way too much equipment, way too much cost, and it's going to be inefficient, ineffectual, and it's not beneficial to the building owner. So we step back, we take a look at the application as a whole and say, okay, how do we optimize this for cost? How do we optimize this for efficiency? And what are the best ways to accomplish these goals? And there's a lot of people working on this. Nyle is deep in this ecosystem, but we are not alone. There are a lot of organizations that are putting out some great advisory tools. There is code that has actually been created now in multiple jurisdictions to guide people on how to actually accomplish this goal in buildings. And it's getting easier as a result. There is more reference, there is more defensibility in designs that we have been talking about for years. Now the applications are out there. The proof has been made. Now it's entering code. Now it's something that can be done on a more consistent basis.
Excellent. I'm wondering if you could talk about, this is a little bit of a segue. I call it load shifting, but a lot of times we're storing the hot water in a tank, right? So that the concept is you want to use as little electricity during the peak on-demand times during the day, right? So if you're in New York City, I don't know what the peaks are in New York City, but if you're in a big city, they probably have a penalty if you use power from such time to such time, right? So with some water heating systems, I don't know if they're all designed this way, but sometimes they're designed in a way that you can load the hot water tanks at night using the cheap electricity. And then have that storage. Because like you said, some buildings, the profile of hot water heat is, 7 a.m. to 9 a.m., then nothing, then 4 to, I don't know what it is. But there's 2 big peaks, maybe 3. But the rest of the time, you don't need to be making water at 3 o'clock in the afternoon or 11:30 in the morning. Can you speak a little bit to that?
Absolutely. So this is one of the really cool areas about heat pump water heating and just water heating in general has been that this kind of awakening in the energy realm, understanding that every building already has a giant battery in it. You don't have to deploy a bunch of electric storage necessarily to start to create grid resilience. Domestic hot water, there are these tanks everywhere, and they are full of energy, and we charge them at varying rates at varying times. And as I said, it's a dump load, right? It runs at very high output for very short amounts of time, recovers, and then is off most of the time. If you can take that energy usage and move it, as load shifting is a fun term. There's also load shaping, where you are just taking those peaks and on the grid and pushing them or flattening them over a longer span of time, right? That can be accomplished by the literally millions of water heaters all spread across the United States. And commercial is obviously a huge opportunity because they have the space to accommodate much larger storage volumes and also the demands that make it very compelling to decrease their energy usage. So we're seeing this on a lot of commercial projects coming up on the West Coast specifically. We're leveraging, there's a standard known as CTA 2045. It's an ANSI standard, publicly available to everybody. And it's a port design with a communications protocol. And in essence, it allows a grid operator, any one of the major municipal grid operators is going to be able to leverage this technology. But it allows them to communicate with these water heaters and say, hey, we're entering a period of time where we might get into grid instability. Please don't use energy during this time. This is the part that most people are a little nervous about. The alternate side, though, is, hey, electricity is really cheap right now. We have an overage on the grid. We need to shed it. Please pull as much energy as you can right now and store it.
Mm-hmm.
And being able to communicate that to, again, a water heater that's got thousands of gallons of storage somewhere, and just take all that energy and max out how much you've got inside that tank. Now you are absorbing all of that inexpensive electricity, but in many ways wasted energy, transferring it. And now maybe you don't have to fire up a peaker plant at 1 o'clock in the afternoon when AC loads are highest, or whatever it may be. If it's wintertime and we're talking all electric heating, we can shift that load as well. So this is it's not seen extraordinary wide deployment yet on the commercial side, but we are actively participating in multiple pilots of this on large commercial buildings, and it's very exciting.
Excellent. We'll have to do another show on applications, because we did one a few years ago, and they're very interesting because they're kind of new, at least in my experience, they are. And I think everybody would benefit from that. So one last thing before we go, I got this great video here from Landon.
Yes.
And maybe we'll play a little bit of this, and you can kind of talk through, in general, like, let's talk about the defrost cycle on air source heat pumps. Talk about that, how it happens, why it happens, and what we do when it happens.
Yeah, so this is one of those areas where heat pumps, traditionally, looking back, they tended to stay away from freezing conditions, right? The heat pump works above 30, 40 degrees, and then you rely on some auxiliary heat below that. Now with this push and technology innovation to allow us to work when it's colder outside, we're encountering new conditions. And so one of those conditions is not necessarily when it's extraordinarily cold outside, below freezing, but between 32 degrees and 40 degrees in humid environments, like near the ocean, very common in the Pacific Northwest as well, that we are actively cooling air at very cold temperatures at high saturation. Guess what happens? You make a lot of ice on your coil. From a thermodynamic standpoint, there is no way to avoid that. I've got cold refrigerant trying to extract heat from a cold environment with a lot of water in it. I'm going to make some ice when I do that. And there's a lot of different approaches to. Whoa.
About that?
No, all good. That was very dramatic. But
like the opening of a big murder mystery movie or something.
I know, all right. Nyle has tried out a wide variety of defrost mechanisms to allow us to handle this problem. This is not unique to any manufacturer. This is just what happens at these temperatures and these humidity conditions. And so this in particular is actually a video of our cold climate heat pump. This is our E360. And it leverages an active defrost mechanism, intelligent defrost. It's actively monitoring for ice conditions and managing the ice on the coil. But it's doing that through a series of electric resistive elements embedded in that evaporator. So you can actually see this happening here in this video. We cycled down our compressor. That whole process takes about 10 minutes for the oil to fully circle around, make sure that we fully pump down. And during that time, we kick on these elements that have less input power than the compressor, so there's no electrical penalty. And we're able to, as you can see here, take out an immense amount of ice off the evaporator in a very short amount of time, and then restart. We get to scavenge some of that heat we just injected into the coil, take advantage of that heat. It's not totally lost, and overall end up with a very efficient defrost cycle. Now, when you talk about differences, right, between space heating and domestic hot water, we deal with dump loads. So turning off a unit for 5 to 10 minutes, and then immediately turning it back on, does not harm our process because we're storing energy at higher temperature than use. We have buffer capacity much higher than what you'd have in a traditional space heat application. And so this defrost mechanism works very well for these applications. And you don't have to deal with hot gas derates. You don't have to deal with reversing valves that actually chill off your domestic hot water in the wrong way. There's a lot of advantages to this method, and we've really proven that out in our process. And this has been the best way, in our opinion, to move forward on these designs.
And quick question for you, Chris, on that. Why is it so important for us to kick off the compressor while we're doing this as far as power usage is concerned, let's just say in California now? And what was a big reason for doing that?
Yeah. So, there's a lot to that question, but at its core, when you are building an all electric building, we're using a lot more electricity than we're used to, right? All of that energy that used to be piped in through a natural gas line now has to come from the electrical side. If you talk retrofit, this is even more sensitive, but just in general, making sure that we are minimizing the electrical impact of the machines is incredibly important. So running a lot of electric strip heat at the same time as the compressor massively increases your electrical draw on these units, and you have to build out even more electrical capacity to the unit. So we've gotten away from that, and this technique, again, it works very well, and it ends up being more efficient from a total on time output capability than any other defrost mechanism we've tested.
Excellent. Well, I think that was a great hour and 2 minutes. I love it. I love the new where you started out in the factory. That was so great. We've only done a few of those, so I'm going to hope we do more of those with you guys. And I hope that people watching and or listening to this got something out of it. I sure did. This is a hot topic right now, so you can check out more of this kind of information at our YouTube channel at HVAC-TV. We're on our podcast, the Engineers HVAC podcast. And Chris and Tomas, thank you so much for coming on. Did you have fun at least today a little bit?
Tons.
Absolutely.
I love doing this. Thanks for inviting us.
Thank you so
You're
much.
welcome. If you guys don't mind, I'm going to play this little timer, let people look at your website here, and there's a YouTube channel link. If you can wait, I'm going to put us all in the waiting room. If we could just come back here in a few minutes to talk for a minute. So thank you all so much for listening and watching our show today. Thank you.